So my talk is FPGA fabric is eating the world, and it's the rise of the custom computing machines. That's seen through my eyes. So take that as just a viewpoint. So first, I'm going to talk about fabric. You know, the fabric is basically all the hardware in a computing system, right? And in the beginning, the fabric was simple: ALU, some controllers. You know, the fabric grew. There are many kinds of fabric. You can see the list here. You can also think about the fabric of a single device. So in the beginning, the devices were simple: ALU and some controllers. And then came mainframe cores, mini CPUs, micro CPUs, FPGAs, and finally GPUs. This talk is going to be about the past, present, and future of reconfigurable computers and the FPGA fabric on which they are based. So I want to define reconfigurable computing as taking a high-level language, compiling it to an FPGA bit stream, and then running those bit streams one after the other. I do that because, you know, there's a lot of reconfigurable computing definitions and whatnot, but for me, it's you take a high-level language and then you use that just like you would any other computer. So from my paper at the first SCCM, you know, I built in '92, I was working on, I had 520,000 reconfigurable programmable gates. That's 52 4010s. And then look, I had a bunch of megabytes of SRAM, which you have in FPGAs today. I had a whole bunch of dual ported RAMs. And then I had a bunch of interconnect on the board that would, you know, because FPGAs weren't so good at routing. But the thing is, I could actually configure the whole board in 25 milliseconds. It was extremely fast, everything configured in parallel. So it was pretty cool. Here's a picture of the board. I built this board. It was a big board. And if you notice, you can see the dual port RAM. You can see the bigger blocks of SRAM. You know, this was a control section, and then it was kind of set in pipelines going across here. And so you see all that stuff in modern FPGAs. So I also, in the same paper, I talked about compiling a program and being able to compile the bit stream directly into the executable. I called that hardware object technology. And you can see the little hardware code. You had loader, config data, IO code, and then you would also have software emulation in case you weren't hooked up to the FPGA. The other thing I put in my first paper, which was kind of interesting, is fused arithmetic. You know, you hear about this all the time now, but back then, I don't remember anybody talking about it. So you could take a huge program and a bunch of operators, and you could actually fuse them in a single compact function. Now, you probably wouldn't do this much that you see here, but the idea is that, you know, just multiplying multipliers, you could have a 3-input multiplier, you could have all sorts of different things that you could do that you can't really do, you know, in a single hardware thing on a CPU because they just don't have the hardware. But here you could make the hardware. So it's very interesting. So now I want to stop for a second. And, you know, we all talk about FPGAs and they're good at computing, but why? Why are they good at computing? Is it just, you know, just happens that way? But there's a couple of fundamental things going on here that makes them good for computing. Number one is there's this dark silicon problem. Now, you don't hear about that with FPGAs. I don't say, oh, FPGAs suffer from dark silicon. That's not how it works, because in a CPU, you have the memories, the caches, but the cores get extremely hot. You know, if you run those cores very fast, they get really hot to the point where they fail. On the other hand, you have FPGAs where you could see that, you know, the logic is spread out. The flip-flops and the lookup tables and things like that are spread out. So you spread out that heat and that power draw on the silicon substrate all over the place. So that way, you know, they're not really as affected, and though they might in the future be affected by dark silicon, but they're nowhere near what CPUs have to contend with. Now, there's another thing that happens with FPGAs, which is pretty interesting, and you all know this, is that you can pipeline stuff. If you use a multi-core system with caches, and memories, you can see what happens is that all the cores want to get to one bank one and get the data out of there, and then they want to put it over into another bank of memory, and then they go back and forth and back and forth, and that just, you know, wreaks havoc on the memory subsystem. On the other hand, with reconfigurable computing, you could pipeline everything. So instead, they have the input data, it pipelines right through your functions, F1 and F2, if you write them correctly, into the output. And then if you want to do another one, you know, you can take that, you can change that output data into input data for the next set of functions. And you can have multiple functions streamline into each other, which each one of these function boundaries here in a normal CPU system, this would have to go to memory and come back. This would have to go to memory and come back. And this would have to come to memory and go back. And so you would have way more memory traffic and therefore less performance. And that's one of the reasons why FPGAs are so great for computing. But there's another one, and it's called Rent's rule. And I don't know how many of you know this, but Rent's rule describes the relationship between the amount of logic in a partition and the amount of communication into that partition. So FPGAs are basically based on Rent's rule and doing a really good job on Rent's rule, and CPUs and GPUs are not. So with a core and a cache, you have hundreds of wires going into that core logic. On the other hand, you've got thousands of wires going into that same amount of area on the die, so you can really get the data into and out of your logic and what you're doing in your computation. So at a very fundamental level, the fact that FPGAs are kind of designed with Rent's rule in mind to get the data in and get the data out is one of the other reasons why it's much better than CPUs, in my opinion, or GPUs for computing. And so there you go. And then, so now I want to talk about the 6 waves of reconfigurable computing. I say there's 6 waves, and I'm going to talk about them. So the first wave was Ross Freeman, right? So he started it all. He did the first successful, commercially successful FPGA. There are others who did FPGAs, but this was the first commercially successful one. The devices use memories and registers and path transistors to create a homogeneous array of lookup tables and logic and changeable routing. Right? The devices were based on SRAM, so they could be reconfigured on demand, which was totally amazing at the time. If you had ever done a gate array, you'd understand. But you know, device support for reconfigurable computing wasn't there. You couldn't just plop a reconfigurable computer, an FPGA down and have it run. It had to have all sorts of other support devices around it. Basically a PAL, you know, so that you could swap in and out, and maybe some memories, the whole configuration. And that's what I did. I put that together. So you know, the invention of the first reconfigurable computing system, basically, I kind of claim that, because when I first did FPGAs, I was building reconfigurable computers. I wasn't building emulators. I wasn't building, you know, some other thing or one-time loadable device that would boot up and stay there forever. My whole goal from day one was to build a reconfigurable computer. So, but my first introduction to FPGAs was kind of funny, because I was in an EDA lab and somebody came up and said, "Casselman, you like weird stuff. Come out and talk to me about this new vendor." You know, the new vendor was Monolithic Memories, which was a second source for Xilinx at the time. And the new part was called Logic Cell Array. And this was before they had schematic capture. So Maya was talking about plinking on, you know, this little editor that they had, and that's how I first started. You know, but I knew right away that it was a new kind of processor. It just had a weird programming model. You know, so I always thought of them as processors. They're not FPGAs, and they're not, you know, you could call it reconfigurable hardware, but to me, they were processors. So, and I was sure that they could be programmed, because there's a basic tenet. Is anything you can do in hardware, you can do in software, and vice versa. So they had to be programmable. In 1986, I wrote my first SBIR proposal. I didn't get that. But I called up Ross Freeman and talked to him. I showed him my proposal, and he said, "Go talk to somebody at the Institute for Defense Analysis." I think that's analyses. I spelled that wrong. I talked to somebody there who said they were doing an FPGA prototype for an ASIC. I told them about my idea and sent them my SBIR paper. And then next thing I knew, they came out with the Splash and the Splash 2. And when I talked to the guy, I said, well, can we sign an NDA? And he said, you know, we don't really do that here. And I go, okay, I don't know. And then he said, well, you know, you could send stuff into this to us and it'll never go out. And my paper didn't ever come out, but what came out was Splash and Splash 2 system, because they stopped making their FPGA prototype for an ASIC and decided that the reconfigurable idea, computing idea, was exactly what they needed. And so I then, the next year, I wrote another SBIR. This one I got. So this I got, and you could see right away, I'm making a supercomputer out of reconfigurable hardware. That's what I'm doing. I'm not, you know, I'm not looking around to see what could be done in some way or another. I knew what I wanted to do. Oh, yeah, this is a list of, in 1986, what happened. I just wanted to throw this in. I mean, this is how long ago it was, right? Challenger, Halley's Comet was coming around, Microsoft had an IPO, Chernobyl, Iran-Contra, and Lady Gaga. She was born in the same year I started working on this stuff, so that's a long time. So now the first wave, what I consider the first wave, was basically my patent. You know, here's my patent in '92. But we won the first SBIR of the Year award. And we were, I believe we were the first commercial company on the cover of NASA Tech Briefs. And then there's a little spiel about us. And for more information, so we won the first, this was the first SBIR Technology of the Year. So everybody for the last decade was eligible for this award, and we won it. And it was pretty funny because there was a guy from Microsoft who came up and said, oh my God, what is this? How many points can I give? 10 points? I want to give him 11. And then he wrote me this letter that said, it started off, it said, I feel like a gushing schoolgirl. I thought I knew everything about computing, but then I saw this. So that's when, in my opinion, that's the first wave. The second wave, lots of conferences, small businesses, early press. In fact, they did a DARPA program, and DARPA said, we will bring you the future. And it was in Scientific America. And we heard about that. And so in that same issue, we offered the future for sale. So there it was, the Xilinx 6200 RPU, we're calling it, reconfigurable processing unit. And it had Lola logic, which was done by Nicholas Wirth. And it was a very interesting kind of constructive language, Pascal-like, very interesting. So we made a deal with a distributor to source all the components for the board. We packaged the board up in the software and sold it back through the distributor. So that turned out to be a pretty good deal for us. And then high-level languages started to come online. You had Handle C from Ian Page. You had the Napa compiler from Maya and Jeff Arnold. And then you had JBits by Steve Guccione. This, in my opinion, is the most important project in reconfigurable computing history, because it allowed you to generate bit streams deterministically in less than a second. So in less than a second, you could have a Java program pump out a bit stream. And what was pretty interesting was, if you had an algorithm and you had some data, you could take that together and smash them together, and you could drop out a custom computing machine based solely on that data. So for example, they did Smith-Waterman, right? And they took the DNA sequences and they baked it into the algorithm, and it was the fastest Smith-Waterman in the world, and it beat out ASICs all over the place. They did the same thing for DES encryption. They took the key and they jammed it into the algorithm, and when they were done, they were the fastest hardware in the world, beating out ASICs. And I think that's an important message. So now the third wave, in my opinion, was when real money came out. Cisco, Juniper, all these guys were doing comm processors. You know, a lot of little small companies got bought up, and we started to learn that AI inference works best on FPGAs, and is in fact kind of a killer app, because the AI, DNNs, CNNs, and those kind of things are moving so fast. The inference part of it maps, you have to map those to hardware all the time, and it's very different. And then, you know, you could do things like reducing the precision. We've already seen that, but I think that's kind of a killer app for FPGAs. So FPGAs deployed in a supercomputer. You know, we got together with Cray, and we took my patent here where you take out a processor and you put in the FPGA, and we sold that through Cray. Now, it was very interesting because right around that time, Cray just spent $100 million for a company called Octiga Bay. And we were looking at it, and I was going, those guys, you know, I don't know. I won't say anything bad, but anyway, then we got them to come into our shop. They looked down at the little processor that plugged right into the motherboard, and then they dropped Octiga Bay. All the $100 million just went down the drain, and they started working with us, and we delivered a lot of these to, you know, the Five Eyes guys. Actually, the US already had their own version, so they didn't buy our stuff, but the Australian and New Zealand and Canadian guys did buy our equipment. You know, and after that, more stuff came online, more programming languages, that it got easier to program. So there's Auto ESL, Jason Kong, you know, that becomes the basis for Xilinx HLS, and there's Catapult C, which was from Mentor. Impulse C was Dave Pellerin, who's now at Amazon. And I used Impulse C to get 80X on a box where I had swapped out the Opteron with an FPGA. And that was part of the puzzle that convinced Microsoft to adopt FPGAs. So that's all pretty cool. So small companies got bought. Molex buys both Bitware and Nalitech. And just looking to see what time is. Micron bought both Pico and Convey. And we got acquired by our biggest customer. So now we're in the fourth wave right now, in my opinion. There's big company buy-in, the Super 7, you know, Azure Cloud. Every node in the Azure Cloud has an FPGA on it. AWS, fourth generation of small businesses start to come out. Today, you see stuff like Swarm 64 and Big Stream, and you know, there's a whole bunch of other little companies that are making nice progress. So, and in fact, what they're doing now is, if you look, I had this patent on the distributed virtual computer. So here it is. And if you see, look, it's got FPGAs going through, all connected together in a token. It was in a token ring. And you could compute on one node and then pass the results to the next FPGA, and you didn't have to touch the processor, because whenever you went back over the bus to the processors, especially at the time when like the S bus from Sun was the fastest bus at 40 megabytes a second, you know, you could, you know, that would kill your performance. So you wanted to stay, you know, in the FPGA realm, all hooked up and all connected. And so you could see that patent was issued on in 2000, and allow you to connect the FPGAs directly together. I wrote a paper, and I had a round trip latency of sub 2 microseconds, and that was a world record at the time. And I wish people would reference that more when they write these papers. You know, I don't get a lot of references. So Microsoft now, as I was saying, Microsoft now uses this in all their new Azure data centers. Every node gets an FPGA. So another thing that I did was combine an FPGA and a CPU. At least the guy got the patent on it. So you can see the patent was in 2001. And here it is. It's a FPGA, a multiprocessor, a controller to control this stuff, and RAM, all in the same package. So it sounds pretty familiar, doesn't it? The device of today. And in fact, my opinion, this is AMD and Intel's current plan, is to mash all this stuff together somehow. So now you got the big company buy-in on the fourth wave. On the fifth wave that's coming, you're going to find total acceptance of FPGAs in the data center. And you can tell that, and here's just Googling that, you know, FPGA in the data center. It's inevitable. Acceleration in the data center. FPGA acceleration in the data center. Data center acceleration. Xilinx. Everybody knows now that the data center is where you want to be because, you know, CPUs were basically built to accelerate a benchmark called LinPack. And in LinPack, you know, you have big caches really help you out because you're reusing data vectors all the time. But in the data center, that's not what you do. You don't really reuse the data too much. You stream the data in, you analyze it, and you don't care about the data after you get the analysis of it. So for example, if you're doing indexing, you stream the data in. And what helps is queues, multiple queues all over the place. And FPGAs are really great at that. It turns out that in a lot of data center applications, you don't need floating point and you don't need anything. You just need to analyze what's there to see what's going on. A lot of this stuff is that very simple structures, and FPGAs are so large that you were see in the last talk, they were just taking up 6%. That's a whole function, 6%. That's nothing, you know. So you can do a lot of analysis as the data streams in. In fact, FPGAs are, you know, single or multiple instruction, single data. They're one of the very few things. You throw the single data stream in, and you can split it up into multiple paths, and then analyze each of those for different things. So single stream in, multiple actions happen in the FPGA. So that was this is just results from the first page, you know? So you've got Xeon plus FPGA, looks familiar. Acceleration, field programmable gate arrays, the ideal choice. Sounds good. FPGAs attracted attention. Oh, really? That's nice. And get data centers get a boost from FPGAs. Yes, they do. And as soon as they're all baked into the data center in reality, that'll be total acceptance. In fact, they're almost already accepted. You almost never see a paper that talks about CPUs and GPUs and they don't mention FPGAs. No, you don't see that anymore. 5 years ago, I remember going to a high performance computing site and they said, CPUs do this, GPUs do that. And I said, well, what about FPGAs? And they said, get out of here. You know, they don't say that anymore. So that's really great progress. So there are more ways now to program hardware. You've got C and C++, OpenCL, OpenACC. And this is the one that is the most important for us today, in my opinion. It's called RapidWrite. RapidWrite is an open source project from Xilinx. Like JBits, you have access to the lowest level of the FPGA. You call out wires, you call out lookup tables, you call out DSP units, and you hook those together with code. Now, what's great about JBits and RapidWrite is what you do is you have this lowest level that's wires and things, but they're generated. So there's not really routing involved. You know, there's no router that comes in. There's no placer that comes in. You do this very low level stuff. And then you go up a level. And because you have overloading and things like that, you go from, you know, A plus B equals C, that all of a sudden becomes hardware. And you can run it as software, and then you can run it as hardware. You can pump out the hardware. And so in JBits, what was great about JBits is they actually pumped out the bit stream. In RapidWrite, they pump out what do you call it, DCP, something like that. It's a, you know, intermediate file. Then it has to go back to the tool. Then you generate the bits and it comes back. You know, so there's a little lag time there I don't really like, and I wish they would get over that. But be that as it may, you know, it's still an extremely powerful. And why is it powerful? So you write a program, and you could do this. It's done in Java right now, but you could write it in C++ and do a wrapper around all the stuff at the bottom. You know, you write a program, and as you run the program, you come up to your hardware, what's going to be your hardware code. It generates a hardware code. It could be based on all sorts of stuff. It could be based on, you know, how many units do you need? What is the ultimate performance that you need? Do you have a data and algorithm cruncher that gets you the ultimate stuff? So, you know, if you have these kind of things going on, so under the same runtime, you generate the design and you use the design. So that's in the same runtime. All these other things that you see here is you write the code, you throw it through their compiler. Sometimes you wait for many hours, and then you have a bit stream, and then you have to load that somehow into your FPGA, and it's different. And, you know, just then you go, oh, I don't like the performance. I'm going to have to do this again. It's going to take me 14 hours to, you know, to even try this again in hardware. With rapid write and programs like this at this level, you want to change, you change a little bit, boom, you run, you've got hardware. It doesn't take any. So there's this example that they do where they take 80 pico blazes, right? And you take them into the Vito, you define them as a partition, as a reconfigurable partition, you place and route the little pico blaze, and then that comes out as a DCP file. And then what you do is you read that in at runtime, they ripple out 80 of these, and then they wire them up. And that takes 6 seconds. 6 seconds. So what does that mean? That means that you could have libraries of precompiled operators and functions, and you could put them together in seconds, right? And you can have, this is the only thing that I can see that would be a just-in-time compiler for hardware, where you could actually, oh, okay. Yeah, all right. As I said, but anyway, you can see I'm excited about Rapid Write IO, and I think you should go there and see it. So in 2008, the vision has always been to have one kind of node. This was from 2008. You can see now you do OpenStack, Swift, Nova Compute. You put the compression and the encryption and the queue and data management all in hardware. Then you can run AI, you can run search. So this is my vision from that time, 2008. It's still valid today, right? But as chiplet technology happens, that lets the fabric absorb everything. So here's the package outline. You're going to have some FPGA in there. You're going to have some memory in there. You're going to have the AMD Zen module. Wouldn't that be great, having like 8 cores of a world-class processor in the package, right? And then if optical processing and interconnect happens, and that's good, that will get sucked into the package. And if a silicon quantum processors happen, that will get sucked into the package. And this is like the future, right? So the future as seen by me here. So many years ago, I did this. It's a wafers, stacked wafers with optical interconnects between them. In the manufacturing, you make a purge map. You use a whole wafer. Every wafer is useful. And this is a vision from 1993 that gets better every day. And so that's just the final slide here. Every area of science must have a fundamental law. Yes, a fundamental law of science. So the fundamental law of FPGA fabrics is, if a compute architecture is useful, it'll be absorbed into the fabric. And we see the history of this: adders, multipliers, memories, high-speed IO, processors, GPUs, photonics, the optical computing comes next, quantum computing after that, Anything that's good and useful is going to be sucked into the fabric. And that's why FPGA fabric is eating the world. Thank you.